6.5, solving exponential equations. So first we've got the property of equality for exponential equations. So if you have b to the x and that's equal to b to the y, so I've got the same base here on both sides of the equation, well then the exponents have to be equal to make this balance out. So that means x would have to equal y. The only exception would be if the base is 0 or 1, then they don't necessarily have to be equal. But otherwise, if you have the same base with different exponents and that's all you have, then you know the exponents are going to be equal. So that brings us to these examples, because now we can solve these. They do have the same base on both sides. So 3 to something equals 3 to something else. Well, that means the something and the something else have to be equal to each other. So I can set x equal to 7. And hey, I just solved that, right? 3 to the 7th is going to equal 3 to the 7th, whatever that is, right? Okay, and then we can do the same, use the same idea here. 3 raised to this equals 3 raised to that. So that means this and that are equal to each other. So I can say x minus 7 is going to equal 2x minus 2. Okay, now this, we've got to do a little bit more work to solve for x here. So I'm going to subtract x from both sides to combine those x terms. That gives me negative 7 equals x minus 2. And then I'll add 2 to both sides to isolate the x. So negative 5 would equal x. And if you like, you can plug in the negative 5 into the original equation to make sure it balances out. Check it. Okay, so that's nice when we have the same base. Of course, we're not always going to have the same base. So here we've got some exponential equation. We have different bases. Okay, this first one, I have 2 to the x equals 8. Now you could just do a guess and check thing here and try some different numbers, and I think you'd find x pretty quickly, maybe in your head. But there's another way we can deal with this. We can rewrite this so that it does have the same base on both sides. So what I'm thinking of, hey, 2 is the smaller base, 8 is the bigger base here. I know there's no exponent, but you could think of it as 8 to the first, right? So I always look at the smaller base and think, can I raise that to some power to equal the bigger base? And I can here. So 2 to the third is going to equal 8, which actually gives me the solution to the problem, I know, but I'm working to doing problems like this towards that. Okay, so now if I can write this side as 2 to the third, well then it looks like this problem up here, right? Now I have the same base on both sides, so that means the exponents are equal, and that means x is going to equal 3. Makes sense, because 2 to the third equals 8, so that's what x has to equal there. Okay. All right, so this one would be a little bit harder to figure out in your head than the previous example, but we can write both sides with the same base just like we did over here. So I've got 2 to the 4x on this side, and I'm thinking, okay, 8, I can rewrite that as 2 to the third. So I've got 2 to the third, and that's still raised to the x plus 4. Okay. So now I want to simplify the right side of this a little bit. When you have an exponent raised to another exponent, you're going to multiply. So just to do a little example off on the side, x to the second to the third, that would be x to the sixth, right? I'd multiply the 2 and the 3, because there would be 3 groups of x squared. So there would be 6 total x's. Okay, so I'm going to do the same thing here. I'm going to multiply 3 times the quantity x plus 4. And I say the quantity because you want to multiply both the x and the 4 by 3. Okay, so now I've got 2 to the 4x is going to equal 2 to the 3x plus 12. I distributed that 3. Okay, now I've got both sides written with the same base with no parentheses, so now I can say 4x is going to have to equal 3x plus 12. Okay, and I can solve this for x by subtracting 3x from both sides, and then x will equal 12. Okay. All right, let's try some more. So this one, I've got 4 as my smaller base, 8 as my bigger base. Well, so I'm thinking, can I write this as 4 raised to some power? Well, 4 to the first is 4. 4 to the second is not 8. 4 to the second is 16. So be careful there. That's not 4 to the second. So I can't take 4 and raise it to the power and have it equal 8, at least not with an integer, with a nice round number. Okay? So then in this case, if you can't take the smaller base and have it set it equal to the bigger base by raising it to a power, then look for an even smaller base. So I'm thinking, is there a smaller base that I can use on the left side? So can, like 2 squared equals 4, right? 2 squared equals 4. So I could write this, and then I can write 8 as 2 to the third, like I did on the previous problems. Okay? So then on both sides, I'm going to take my exponent and multiply by the other exponent. So 2 to the 4x on the left. And on the right, I want to distribute the 3. So this is going to be 2 to the 3x plus 3. Okay? And now I can set the exponents equal to each other. 4x will equal 3x plus 3. And we'll subtract 3x from both sides. And then x equals 3. Okay? Let's try another here. So 9 to the first is 9. 9 to the second is going to be 81. So I can't get a 27. So then I'm going to look for a smaller base. So I'm thinking, what would be something that I can raise to a power to get 9? Well, 3, right? 3 squared is 9. And then 3 to the third, 3 times 3 times 3 is 27. So I can write both sides with a base of 3. Okay, I'm replacing 9 with 3 squared. I'm replacing 27 with 3 to the third. Okay, and now I can simplify this, write it without parentheses. This would be 3 to the 2x, and this would be 3 to the 3x plus 6. Don't forget to distribute there. Okay. Now I'll set those exponents equal. Okay, I'm going to combine my like terms. So this is going to give me negative x equals 6. But I want positive x, so I'm going to multiply or divide by negative 1. And then x equals negative 6. Okay. So this is a little bit of a review on these couple problems, but you need to know how to do these to do the problems that I'm going to get to in a second. So let's rewrite with a positive exponent. X to the negative 6th would be the same as 1 over x to the 6th. Okay, and likewise, this quantity, 2x raised to the negative third, is going to be the same as 1 over the quantity 2x to the third. Okay, so you could write like that. If you wanted to write it without parentheses, you'd want to cube the 2 and the x. So 2 to the third is 8, and x to the third is x to the third. So that's what it would look like completely simplified there. Okay. All right. So if you notice these, you put 1 over something, and then it's with a positive exponent. So you can do this in the opposite direction. 1 over x to the 8th. Well, if I move this x to the 8th up into the numerator, then it's going to become x to the negative 8th, right? So if you wanted to write that with a negative exponent, it would look like this. And this would become the quantity 3x to the negative second. Okay, and then again, you could distribute the negative if you wanted to. So you could say 3 to the negative second times x to the negative second. Okay, so that brings us to these problems. So you'll notice these last 4 problems, all of them have 1 over something. And whenever I see the 1 over something, when I'm trying to write both sides with the same base, I'm thinking, oh, I can use a negative exponent. Okay. So what I would think here, I'm on this first one, I'm thinking, can I take 3 to some power and have it equal 27? All right, 3 to the third is 27. 3 times 3 times 3, right? So I could write this like so. It's not written with the same base yet, but I can get it to have the same base by moving the 3 to the third up into the numerator, and then it would become 3 to the negative third. So now I can say 3 to the x equals 3 to the negative third. And now I have this written with the same base on both sides, and so then x is going to equal -3. Okay. On this one, I'm thinking, okay, I've got a 4 over there. Can I take 4 to some power to equal 16? Well, 4 to the second is 16. So I can say 4 to the x plus 2 equals 1 over 4 squared. And now I can pull this up, and it'll be 4 to the -2nd. Okay, now I've got both sides with the same base, so I can set these exponents equal to each other. I'll move off to the side here because I'm running out of space. So x plus 2 would equal -2. And then to isolate x, we'll subtract 2, and x is going to equal -4. And as always, you can always check your answers by plugging them into the original equation, seeing if they work. Okay? All right. So same kind of deal here. I'm going to take, I'm thinking, can I raise 4 to some power to equal 16? This is very similar to the last problem, but it's 4 squared, right? So I can say 1 over 4 squared, and this is all still raised to the x, is going to equal 4 to the x plus 3. Okay. All right. So now I can rewrite this side without a fraction if I think of it as 4 to the -2nd. So 4 to the -2nd, that's all still raised to the x, is going to equal 4 to the x plus 3. Okay, and then I want to multiply those exponents together. And now I'm ready to set the exponents equal to each other. 4 raised to something equals 4 raised to something else. So the something and the something else have to be equivalent. Okay. And then I'll subtract x from both sides here. And I've got -3x is going to equal 3. And then I'll divide by -3. X will equal -1. Okay. All right, let's try one more here. So I've got 5 as a base here. Well, the 25 I can write as 5 squared. So 1 over 5 squared, all raised to the x, equals 5 to the x minus 1. And then I can rewrite this as 5 to the -2nd. Okay. Then I'm going to multiply the exponents together here. And now I'm ready to set the exponents equal to each other. So -2x equals x minus 1. Now I've got -3x equals -1. And I'm going to divide by -3 to finish solving. That means x is going to equal, well, I've got a negative over a negative, so that's going to come out positive. So positive 1/3 is my solution there. Okay, that's the end of the section, and I'll see you next time.